Hi guys, welcome to a channel that gives you the opportunity to study or learn in the comfort of homes at your own time and pace. And I hope you are enjoying the videos that I'm giving you on this channel. If you are, don't forget to subscribe guys. Guys, welcome to our second video in electrical engineering technology, and in this video we are going to look at direct current circuits. This involves series, parallel circuits, power, energy, electric energy, voltage source, etc. As usual, your presenter is Motion Marfu. For any information on anything related to your learning in any module, don't forget to get in contact with me on my email address as well as on my WhatsApp number. Guys, it is my hope that you are going to enjoy. We are now beginning to study in more detail electrical engineering technology, starting with direct current circuits. In short, they are referred to as DC circuits. Let us enjoy. This is what you must be able to do at the end of this video presentation. Number one, draw circuit diagrams using schematic symbols. Describe the effect of the internal resistance of a voltage source on terminal voltage. Find total resistance of series connected and parallel connected resistors. Then state and apply Ohm's law in circuit calculations. You must also be able to state and apply voltage divider rule as well as current divider rule in current and voltage calculations respectively. Then you must be able to find total resistance of series parallel connected resistors. Then last but not least, you must be able to calculate power and electrical energy in electrical engineering. These are very simple objectives, and guys, you've got my assurance that you'll be able to do this before the end of this short lecture. Let us enjoy. Circuit symbols are also known as schematic symbols, and as I emphasized in electronics, these must be known because they are the ones that are used when we are drawing circuits. So guys, take note of the schematic symbols. This is for a DC voltage. As you can see, this is a battery, a resistor. This is a resistor, but to be specific, it is called a potentiometer. Then this is a variable resistor or a rheostat, a lamp. As you can see, guys, take note of the earth or the ground. You can use this or this. Then when wires are joined, the dot shows joined wires. These are not joined wires, but they are just across the wires. Then this also represents joined wires. Take note of a polarized capacitor of fixed value, a variable capacitor. Then the symbols for inductors. A variable resistor is also fixed value resistor. Then there's an earlier version of the symbol of a resistor. You'll see that when we do our calculations. Then an AC voltage, this shows an AC voltage. Then a battery, a single cell, some switches, single pole, single throw, single pole, double throw. Then circuit breakers, guys, voltmeter. You must know this, an ammeter, measuring current, and also an ammeter. Then these are the symbols for transformers, speaker. So the list is not limited to all of these. We've got many types of schematic or circuit symbols. Because we are looking at DC circuits, it is important that we have a look at basic circuit conditions because this will determine the operation of the circuit. So we'll start with open circuit. We've got two types of open circuits. When the switch is open and when also the wire or one or more components are defective, thereby not allowing current to pass through. When a circuit is open, it means there's a break. If the switch is off, like in our houses, there won't be any light unless you turn the switch on. Hence we call that an open switch. As you can see, this switch is open, it is off, hence the light will be off. Then the second scenario is when the one, let's say if this bulb bends, even if the switch is on, this will be an open circuit because no current can flow through a bent bulb or a bent light, and this is the circuit has become open or it has been bent out. The other two circuit conditions is when the switch is closed and when there is a short circuit. Basically, what is a circuit? A circuit is the path followed by current from the source and back to the source. So in this scenario, the switch is on. In other words, it is closed, and when you close the switch, if the light is not open or the bulb is not open, as you can see, there is some light being emitted. So this is a very good example of a closed closed circuit or a closed switch, the light will glow assuming if the path is complete and also no defective component. Then this guy called short circuit is when high current flows in a circuit, and this is a dangerous condition. It can also cause or can result in fire. Let's have a look at our circuit. There is a short circuit across R3, which means our conventional current from the source is going to flow through R1 and R2, but it will not pass through R3. Why? Because it will see an easy path or current through this short circuit. Hence, the current through R3 will be 0. So this is a short circuit. Please take note that current flows through or prefers path with least resistance. So if we have a short circuit across a component, no current will flow through the component. All of the current will go through the load. Hence, the total resistance, the effective resistance in this circuit is R1 plus R2, since it is a series circuit, and this one will be of no effect. Please take note. Energy, work, and power. These are some fundamentals that we are going to look at in this video presentation of ours. And what is energy? From our eyes to energy is the capacity, ability to do work. For example, to light a bulb, to heat a room, to move something, energy is required, and it exists in many forms: electrical, mechanical, chemical, and thermal, light, etc. What is kinetic energy? Kinetic energy is a form of mechanical energy, and it is the ability possessed by a moving body, such as a ball rolling down a hill. Then the other form of energy that is also important is potential energy, and this is energy possessed by a body because of its position, such as the ball at the top of a hill that hasn't started rolling possesses potential energy, and when it starts rolling, that potential energy is converted to kinetic energy. So energy is very, very important. We've got what we call law of conservation of energy, which states that energy cannot be created or destroyed, but it can only be changed from one form to another. Please take note. You might be asked to state the law of conservation of energy. So in physics, energy does not disappear. Then we've got some devices that change energy from one form to another. For example, an electrical generator, in case power utility because of one reason or another cannot supply power, we can make use of the electrical generators, and these generators convert mechanical energy to electrical energy. The bulbs, the lights, they convert electrical energy into light energy. That electrical energy will be coming from, for example, the power utility. Then we've got batteries on our laptop smartphones, even on motor vehicles. It is converted from chemical energy to electrical energy. We are going to look at electrical energy, which is measured in kilowatt hours in electricity. We are now looking at electrical energy in particular, and it is measured in kilowatt hours. You know, kilo is 10 to the power 3. And how do we calculate energy in general? That is, in physics, energy is power times time, and in electricity, we know that power is equal to voltage times current, that's VI. This time, take note that when we are calculating electrical energy, we are not using the SI unit of time, which is seconds. We use hours, for example. We've got a very good question which reads: a 500 watt heater operated for 10 hours. Find the cost of operating the heater at 60 cents per kilowatt hour, which means we must convert. First, we need to find kilowatt hours, that is energy. So if we say 500 watts times 10, which is the number of hours the heater is run, we get 5,000 kilowatt hours. And at a cost of 6 cents per kilowatt hour, if we multiply the two, we get 30 cents. That is the cost. Please take note that, as I said, if the power is measured in kilowatts and the time it is used is hours, then the unit of energy is kilowatt hours. And this is the often used unit of electricity when we pay power to our utility companies. Another important parameter is work, and work is done when a force is applied to something and that something is moved through a distance. Force is measured in Newton meters or in joules. If a force is applied and there's no movement, then the work done is zero. So how do you calculate work done or work? It is force times distance, and force is measured in newtons and distance is measured in meters. And please take note, as I said, if no distance is moved, then the work done is zero. Another important parameter, which is a fundamental of electricity, is power. What is power? Power is the rate of doing work or the rate at which work is done or the rate of energy conversion. Please take note. And how is it calculated? It is calculated by dividing work done, energy, by time. So P is equals to W. W is a symbol for work or energy. So we divide it by the time taken. Please take note. The unit of power is watt, which is the rate of working of 1 joule per second. You must be able to define watt, so that is the formula, and guys, you must know it. Electric power is defined as the rate at which work is done as current flows through a wire. A look at a voltage source. A battery is a good example of a voltage source, and also a DC generator or a DC power supply. These devices do not produce a perfect constant output voltage. Why? This is because they've got an internal resistance inside them. The internal resistance is found inside the voltage source, and we'll represent it by small letter r. And please take note that an unloaded power supply is a power supply to which no load has been connected, and the voltage supplied by a voltage source is called an EMF or open circuit voltage. And when a power supply or a voltage source is loaded, the voltage at its terminal voltage, or the voltage found at its positive and negative output, is called terminal voltage. So terminal voltage is the voltage at the terminals of a voltage source with load connected. And please take note of the following important points. The open circuit voltage of a voltage source is equal to its EMF. The terminal voltage source is less than the EMF. This is because some of the voltage is going to drop because of flow of current across the internal resistance, small letter r. So terminal voltage V is equal to electromotive force E minus IR, where R is a small letter r and the voltage drop across the internal resistance. You'll see in the next slide how internal resistance of a voltage source is indicated. When we connect a load resistor RL to the voltage source, the terminal voltage source V will change if our load resistor changes, meaning it drops if our load. Practically every voltage source has got an internal resistance, and it is very, very small. So the terminal voltage V across a load is electromotive force E minus IR, where IR is the voltage drop across the internal resistance R. How do you calculate I? I is equals to the electromotive force E divided by the total resistance of the circuit, which is equal to the internal resistance of the source R, small letter r, plus load resistance, which is equal to RL. If we change the load resistor RL, like in this case, it means that I is also going to change depending on whether we have reduced or increased the value of the load resistor RL. This is the reason why, and I want to emphasize this point because it is important. This is why the terminal voltage of a practical voltage source is not possible to keep at an ideal constant value, because RL will be changing. And in practice, please take note, internal resistance small letter r is far much less than the load resistance RL. Otherwise, all our voltage would drop across the internal resistance, and very little will be left to power up our load. And our aim is we want all the EMF to power our load satisfactorily. Because this is far much less than this, it means that the voltage drop across the internal resistance, which is I small letter r, is very small, and therefore we can say terminal voltage V is almost equal to the source voltage E, which is the EMF. You will see when we work out some examples that they are almost the same, because E, which is the terminal voltage, because the drop across the is the terminal voltage V, it is in most cases less than 1. an illustration of a practical voltage source. We've got a source of EMF 4 volts and an internal resistance of 0.1 ohm. As I said, the internal resistance, small letter r, is very small. So if no load is connected between the points A and B as shown, the voltage across A and B is what we call the open circuit voltage. You know what an open circuit is, and this open circuit voltage is equal to E. Why? Because no current is flowing. It means that the potential difference or the voltage drop across R is zero. Please take note. That's a very important point. The moment we connect a load across, or the moment we complete the circuit by connecting a load across AB, it means that current is going to flow and there's going to be a drop across small letter r, although, as I say, it is small. More on a practical or real voltage source. This time, guys, we have connected a load of 2 ohms across the terminals A and B, and the terminal voltage in this case is equal to V. And how is it calculated? It is calculated by subtracting the drop across the internal resistance, small letter r, from the voltage source EMF, which is equal to E. Or, guys, you can simply say 2, this is what called the voltage divider rule. Don't worry, we are going to have a look at it. 2, which is the resistance of R, multiplied by the voltage source, which is 12, divided by the sum of the effective resistance, which is 2 plus 0.1. This, if you divide this, you must get 11.25. This is an easiest and quickest way of finding the terminal voltage, which is equal to A and B. And please, as I said, if you load a voltage source, the terminal voltage will be less than the voltage source. So 11.25 is less than 12 volts. Why? Because the voltage or some voltages dropped at the internal resistance. So effectively, if this is our smartphones, it means that it will be powered by 11.25 volts. So it means that practically R must be very, very small, so that most of the voltage is developed, or this is developed across our load. Or the longer way that you can do, guys, is to first find current. How do you find current? Current is voltage divided by resistance. So you say 12 divided by total resistance. This is a series circuit. This is 2.1. So if you divide this, you get 5.71. So to find the drop across, the potential difference across R, you say 0.1 times 5.71, you get 11.225 volts. Guys, make use of calculator and confirm these. So what is the voltage drop across R? As I said, it is small because R is small, hence it is 0.75. If you subtract this from this, you get 11.25. So this is accurate. Take note of the following important points. Source voltage is our EMF. Open circuit voltage, which is an unloaded voltage source, it is equal to EMF. But terminal voltage, which is the voltage drop across a load connected, it is less than EMF because of the drop across the small internal resistance of the voltage source. You might be asked the question, explain why it is important for the internal resistance of the voltage source to be small. Guys, I don't know how I should emphasize it, but this law or theory is important. Actually, all other theory based on it, and we call it Ohm's Law, and it was discovered by George Ohm. And it states that the current flowing between any 2 points in an electric circuit is directly proportional to the potential difference across the 2 points and inversely proportional to the resistance of the circuit between the 2 points, provided the temperature remains constant. Guys, I would prefer you put it that way. So what are we saying? We are simply saying if we increase the voltage across a load or across any 2 points, which can be across a resistor, we are also increasing the current flowing through it, provided our resistance remains constant and also temperature remains constant. Mathematically, it is stated as current I is equal to V over R, and it is measured in amperes. You can also state it as V is equal to IR, or V over R is equal to I, whichever way you like. But mathematically, I is directly proportional to V and inversely proportional to R. That is to say, the ratio of the potential difference between any 2 points of a conductor to the current flowing through them is constant, provided the temperature of the conductor and also the resistance remains a constant. And please take note that Ohm's law can be applied to the whole circuit or to a part of the circuit. And if it is being applied to the whole circuit, it means we are going to use the EMF. But if we apply it to a part of the circuit, the resistance of the entire circuit and the voltage across that circuit must be applied. It does not apply to nonlinear devices such as diodes and voltage regulators. Please take note. Ohm's law has got some limitations, and these are, as I said in the previous slide, it does not apply to nonlinear devices such as Zener diodes and voltage regulators. Also, it does not apply to non-metallic conductors, and also it is true at constant temperature. And if temperature changes, it is no longer applicable. A worked problem for you: determine the voltage which must be applied to a 2 kilo ohm resistor in order that a current of 10 milliamps may flow. V is equals to IRI. Our I is equals to 10 milliamps. You need to know your metric table. Milliamps 10 to the is equals to 10 to the power minus 3. Then kilo is equal to 10 to the power 3. So 2 kilo ohm is equal to 2000 ohms. If you multiply the 2, you get 20 volts. The other question: what is the resistance of a coil? Resistance is inversely proportional to I. But so in that case, we are going to divide V over I to get R. That's 220 is our V, and our I, 50 milliamps, is equal to 50 times 10 to the power minus 3. Guys, solve that. Punch your calculator. 220 divided by 50 times 10 to the power minus 3. You must get 4,400 or 4.4 kilo ohms. Summary of Ohm's law: current and voltage are directly proportional, but current and resistance are inversely proportional. Electrical power calculations. Guys, you must give this slide the respect it is due, because let us go. The basic formula of calculating power in electricity or in electrical engineering is voltage times current, and the unit is watts. Guys, from Ohm's law, which we have just looked at, V is equal to IR. So if you substitute V by IR, the result is going to be V is equal to I squared R. If you make I the substitute of the formula, you divide both sides by R as we have done, then you take the square root of both sides. Therefore, I is equals to the square root of P over R. This means that when you are given power and resistance, you make use of this formula to calculate your current. This does not end there. Still from power. From this formula, we can see that R is equals to P over I squared, which means that when you are given power and current, from that you are able to determine the resistance. Hence, this is the formula for calculating resistance from power and current. Power from voltage and current, and a current given power and resistance. Right? That same formula, if we substitute current is equals to P divided by power divided by voltage, which means if you are squaring, we are also squaring this. If you simplify this, it means that V squared is going to go to the numerator, and this P squared is going to remain. Top P and the bottom P are going to cancel. So your result is, when you are given resistance, you can calculate, when you are given voltage and power, you can calculate resistance. Again, when you can also calculate voltage from power and resistance. If you follow mathematics, it means that voltage is equal to the square root of power times resistance. Hence, my statement, you must give this slide the respect it is due, because it is so important. Right? We have looked at the one formula for calculating power and derived the rest. The other formula for calculating power is, as I said, I squared R, and this is how you derive it. I think I've explained this. Power is equals to VI, substitute V is equals to IR, hence power is equals to I squared R, given current and resistance. You will see it when you apply Ohm's law and even other DC theorems. Then the other formula for calculating power is also derived from VI. This now we are using Ohm's law to calculate I. I is equals to V over R. If you simplify this, power is equals to V squared over watts. So guys, make sure these are at your fingertips, because you might be asked to demonstrate that power is equals to V squared over R. You must do that from the formula of power is equals to VI. a worked problem for you so that you are guided on how you tackle such question. A current of 5 amps flows in the winding of an electric motor with a resistance 100 ohms, and you are asked to determine the voltage across the winding. You simply use Ohms Law. V is equals to IR. I is 5 and R is 100 ohm. If you calculate, you must get 500 volts. Practice, guys. Then P is equals to VI, or you can use I squared R. So V is equals to, we have calculated it is 500, and you multiply by 5, you get 2.5 kilowatts or 2500 watts. And you can prove that using P is equals to I squared R, which is equal to 2.5 kilowatts. The disadvantage of using this formula, of using V from a calculated value, is that if you make an error of calculating your voltage, it means that you are going to use a wrong answer to calculate power. So you will miss 2%. The simplest method is to use the values that you are given. Then you prove that using the other formula. Another worked problem for you, not difficult at all. A battery of 12 volts has a load of 40 ohms connected to each. Determine the current in milliamps flowing through the load, the power consumed, and also the energy dissipated in 2 minutes. Guys, think you are now familiar with your basics. From Ohm's law, I is equals to V divided by I. So 12 divided by 40. This gives you 0.3 amps, and if we convert this to milliamps, must be able, I emphasize, to do that. Gives you 300 milliamps. Then how do you calculate power? Power is equals to VI. We've got a V of 12 volts and an I of 0.3. It gives you 3.6 watts. You always use the calculated value in this case. Then let's go to energy dissipated. Energy is equals to power times time. We've calculated VI 3.6 hour time. Make sure you are aware of the SI unit of time, and this is in seconds. So we say 2 times 60 seconds. 1 minute equals 60 seconds. Your answer must give you must get 432 joules. Guys, make sure you are getting these values. If any of those values is wrong, you can show that on YouTube comments and also on WhatsApp, or even to drop me an email in my inbox. I hope you are enjoying. If so, subscribe, guys, if you haven't done so. Guys, once you fail to understand resistors in series and in parallel, then that's the end of your EET, electrical engineering or circuit theory course. So make sure you understand resistors in series and then resistors in parallel, because that's the best. We've got a circuit there, the EMF is V volts, and the voltage drop. We've got 3 resistors. Let me start with the resistors, and these resistors are connected in series because they are connected in cascade, end to end, or one after the other. In other words, they've got one point in common. This and this are joined there, this and this are joined there. Hence, we are saying the same current flows. There is no other pathway for current except this path from the positive terminal of the voltage source through the load and back to the negative terminal. So there is only one path, which means the current through R1 is the same as the current through R2 and R3, and it is designated as I. I times R1 gives you the voltage drop or the potential difference across R1. I times R2 gives you the potential difference across R2, which is equal to V2, and I times R3 gives you the potential difference across R3, which is equal to V3. And please take note that V1 plus V2 plus V3 gives you V volts as stated there. If we substitute the voltage drops with the above equations, IR1 plus IR2 plus IR3, then what are we going to do? We know that voltage divided by total resistance gives us total resistance, but V is equals to current times total resistance. So what are we going to do? We are going to substitute V there by IRT, and we divide throughout by I. So we've derived the formula for calculating resistance in series. Please take note that it is equal to R1 plus R2 plus R3 in this case, but we can continue and say plus R, and where N is the number of resistors connected in series. Guys, take note of this formula and master. Guys, the following characteristics are very, very important, and they must be at your fingertips, must be known by heart. What are the characteristics of a series circuit? The same current flows through each resistor, and we can say current is common, current is the same. Then supply voltage or the EMF is equal to the sum of the potential differences of voltage drops across each resistor. That is V is equal to V1 plus V2 plus V3, or we can state it as E is equal to V1 plus V2 plus V3. Then the other characteristics is the total resistance is equal to the sum of the individual resistances as we derived. Then the total resistance is greater than each individual resistor in the circuit, or we can put it the other way as total resistance is greater than the largest resistor in that particular circuit. Power is additive, which means power from the source is equal to the power dissipated by each resistor. Then the voltage drops are additive, V1 plus V2 plus V3. That is what we mean. Guys, I like this slide. I love it. I hope you are also loving it. And if you are doing so, if you haven't subscribed, we are now going to look at series circuit disadvantages. And these are: if a break occurs at any point in the circuit, no current will flow. In other words, the whole circuit goes down. It becomes useless. So it is rarely used in practice, especially in our homes. Imagine if one bulb goes, everything at home cannot function because of that. So that is a disadvantage. Let's have a look at the second disadvantage. We are saying we've got 5 lamps each rated to 230 volts, and if we connect them in series, it means that the supply voltage must be, in that case, 1150 volts, but our power utility supplies only 230 volts. So it means a series circuit, even for our lights, is not practicable for lighting. Guys, that is a very good explanation. Then the last point we can say, since electrical devices have different current ratings, we know the current rating of the television is different from the current rating of your transformer or of your hi-fi. So it means they cannot be connected in series for efficient operation. Guys, what else do you like? These are very good and understandable disadvantages. Take note. To reinforce series circuits, we've got a word problem, and we've got a circuit there, and according to the problem, we've got 3 resistors, R1, R2, and R3 with the following voltages respectively: 5 volts, 2 volts, and 6 volts. And we are being asked to find the total voltage, total resistance of the circuit, and we saw that the total resistance of the circuit can be determined from Ohm's law, which is equal to V divided by I. So we want to calculate our V. V is equal to V1 plus V2 plus V3 as this is the supply voltage, and it is equal to the sum of the potential drops. So if we add the 3 voltages, we get 13 volts. So this is equal to V. So from total resistance RT is equal to V divided by I. So we have got voltage divided by current. 13 volts, we are given current as 4 amps, so we divided by 4. This gives us 3.25 ohms. This is our total resistance. So we have done part B as well as part A. We are now going to part C. The values of the resistors are 1. Because we've got V1 is equal to 5 volts and current is the same. We simply divide 5 volts divided by 4. This gives us 1.25 ohms. This is the value for R1. The value for R2, we divide B2 by I. Because current is common. 2 volts divided by 4. This gives us 0.5 ohms. Then R3 is equal to V3 divided by I. 6 divided by 4. This gives us 1.5 ohms. So once you do that, guys, you know you get all the marks. That's the way how you tackle that one. Another waved example on series circuit. This time we've got a circuit T, the supply voltage E is equal to 12 volts. Then we've got 3 resistors in series, 4 ohm, 9 ohm, and 10 ohms, and we are asked to find the current flowing through the 9 ohm resistor. And how are you going to proceed? It means that first we must find total resistance. And how do you do that? R1 plus R2 plus R3, 4 plus 9 plus 11. This gives us 24 ohms. Once we get 24 ohms, then we can calculate the current flowing through the 9 ohm resistor. In other words, we are being asked to find current I, which is the current flowing in the circuit. So if you divide I is equal to V divided by R, this gives us 0.5 amps, which is equal to 500 milliamps. Then the other part is asking us to find the voltage across the 9 ohm. You simply multiply the current I times 9 ohm. Then what you get? We get 4.5 volts. We are also being asked to find the power dissipated. The power is equal to VI or I squared R. Then now that we've got the voltage 4.5, we can multiply it by our current, which is called 0.5. Or you can prove that also using I squared R. So you will see that your power dissipated by the 9 ohm resistor is equal to 2.575 watts. This is interesting, guys. So do subscribe. Guys, we are going deeper and deeper, and I'm loving it more and more. This time, potential divider rule or voltage divider rule. Potential is another word for voltage, and we've got a series circuit as shown. V is the applied voltage, EMF, and R1 and R2 represent the voltage drop or the potential difference across the two resistors respectively. I is the current flowing in the circuit, and it is determined by the resistance or the sum of the two resistors because they are connected in series. So we can safely say V is equals to IR1 plus IR2, or we can say V is equals to V1 plus V2. How to determine I is equals to V divided by R, and how to determine R in this case is R1 plus R2. Take note of this formula. We are going to use it somewhere. V1 is equals to IR1, but I is equals to V divided by R1 plus R2. So we are going to substitute I by V divided by R1 plus R2. Then our R1 remains. And normally this is stated as R1 divided by R1 plus R2 in brackets divided by V. This is what we call potential divider rule or voltage divider rule. You are finding the voltage drop across the resistor without first finding the total current flowing through the circuit. The same applies for V2. What do? You say the value of that resistor R2 divided by the sum of the resistors in that series circuit, and you multiply rather by the supply voltage V. So this is what we call voltage divider circuit. And take note of the key points. The voltage drop across any resistor or a combination of resistors in a series circuit, how do you find it? It is equal to the ratio of that resistance value, R1 or R2 in this case, to the total resistance, which is R1 plus R2, multiplied by the source voltage. And as I said, this is voltage or potential divider rule. Guys, I'm loving it. Guys, I'm loving it, and I also hope you are loving it. We are going deeper and deeper, as I said, this time with a worked problem of our own voltage divider rule. We've got a circuit, EMF 60, 3 resistors, 10, 20, and 30, and we are asked to determine the voltage across each resistor, and we are going to use the voltage divider rule. We won't go the long way by first calculating total resistance, total current, and we multiply the current by the value of each resistor. No, it will take us ages. How to calculate VR1 using voltage divider rule or potential divider rule? You simply say that the value of that resistor R1 multiplied by the supply voltage divided by sum. 10 times 60 divided by 60, 10 volts. Let's go to VR2, which is the voltage drop across R2. We simply say that resistance value R2 times supply voltage divided by the same sum, which is the same as this. 20 times 60 divided by 60 gives us 20 volts. VR3. The resistance value R3 times supply voltage divided by the sum of the resistors in series, then it gives you 30 volts. More and more concepts are coming, and we haven't started yet. This time it's parallel circuit. What is a parallel circuit? Resistors are connected in parallel if they are connected across each other. That is, they've got 2 points in common connected together. This point and this point are connected at this point, this point, this point, and this point are connected at this point. The same applies to this side. They are connected at this point. So we say the two resistors are connected in parallel. That is, there is one terminal of each that is connected to form a junction. The terminal of this and this and this are connected together to form one junction, and the other ends are also connected together to form another junction at this point. Please take note of the following properties or derivations. We are saying I is branching into I1, I2, and I3. Hence, for a parallel circuit, we've got more than one path. And what are we saying? Depending on the value of the resistor, that also applies to the variation of the current flowing through each resistor. So in this case, we've got three paths. Each current has got its own separate path, and the voltage across each resistor is the same as the supply voltage. Pay attention to this point, it is very important. Our V is connected to this point and this point, so we are saying the voltage across R1, R2, and R3 is equal to the supply voltage, which is equal to V in this case. So we can safely say V is equal to IR1 and is equal to IR2 and is equal to IR3. But we know that I1 is equal to V over R1, I2 V over R2, I3 V over R3. So we can, and we also know that supply current I is equal to I1 plus I2 plus I3 because it is branching. We can replace these three currents using Ohm's law. It becomes V divided by R1 plus V divided by R2 plus V divided by R3. If we factor out V, it remains like this. But please take note that we know that V is equal to IRT. That is, our supply voltage is equal to current times total resistance. So it means our I is equal to V divided by RT if we make I the subject of the formula. And if we divide throughout by V, this gives us 1 over V is equal to 1 over RT, where RT is equal to this. So we can safely say 1 over V is equal to 1 over T, which is equal to this. If we've got more than 3 resistors, we say plus other resistors until the last resistor, which is equal to N. This is the formula for calculating total resistance in a parallel circuit with any number of resistors. So to find total resistance, it means we must find the inverse of this. After adding, you find the inverse, you calculate total resistance. You will see when we do when we have got two resistors connected in parallel, we've got a simplified formula which we know from our high school. 1 divided by, this is the formula for calculating two resistors in parallel, but we can simplify it as, if you find the common denominator there is R1, R2, then you simplify this, and if you find the total, the inverse of each side, you will discover that for two resistors connected in parallel, the formula is product divided by sum. We are now going to have a look at the characteristics of a parallel circuit from our derivation, and we saw that the formula, the voltage is the same across each resistor. The total current is equal to the sum of the individual currents because it is branching. The reciprocal of total resistance is equal to the sum of the reciprocal of the individual resistance. That is, if you find the reciprocal of 1 over RT is the same as finding the reciprocal of the sum, or the reciprocal of the sum. That's correct. Then total please take note, this is a very important point and I like it. Total resistance is smaller than the value of the smallest resistor, then the last one, but not the least one, is powers are additive. Parallel circuit advantage. Please take note that this is important and compare it to series circuit disadvantages. And we are saying the first one is the electrical appliances with the different ratings of voltage and currents can be connected in parallel without affecting each other's performance. This is a very important point. Then, if a break occurs in any branch, it will have no effect on the other branches. For example, if a bulb in one of the rooms blows, it does not affect the bulb in the other rooms. Because of those two advantages, electrical appliances in our homes are connected in parallel. We can switch on off any light or appliances without affecting other lights or appliances. Please take note. This time again, we are going to look at yet another more concept in our DC circuits. This time it's no longer voltage or potential divider rule, but it is now current divider rule. Why? Because current is branching. We've got a parallel circuit there, and our total current IT is branching or is dividing into I1 and I2. We want to find out how you can simply calculate I1 and I2 using the current divider rule. Guys, as usual, I start from derivations so that we get the nitty-gritties of the concept. I don't want you to cram. So what are we saying? We are saying IT is equal to I1 plus I2, and we are saying the voltage across R1 is equal to V, the voltage across R2 is equal to V. So we can safely say I is equal to V divided by R1 and I2 is equal to V divided by R2. And because of that, we can safely say V, which is equal to the supply voltage, is equal to I1 R1, and this is also equal equal to I2 R2. If we make I1 the subject of the formula on these two equations, want to make I1 the subject of the formula, this is going to be the formula for calculating I1. If we substitute this in this equation, it becomes IT is equal to the value of I1 plus I2. Therefore, we can safely say I2, which is this I2, is equals to IT times R1 divided by R1 plus R2. Or we can also say I1 is equals to total current multiplied by the opposite resistor times the sum of the two resistors. This is for current divider rule, where two resistors are connected in parallel. So take note of the key point. We can say the current in any branch, let's say you are asked to state it. The current in any branch is equal to the ratio of the opposite branch resistance to the total resistance multiplied by the total current multiplied by the total current in the circuit. Guys, take note of that form of that theory or law, because you need to apply it here and there, even when you do some DC. We've got a problem on current divider rule as usual. After a concept, we must apply it. Then this time we've got this circuit and we are given R1 is equals to 10, R2 is equals to 20, and supply voltage is equals to 50 volts. So how do we first to find the magnitudes of the currents or of the total current and current through R1 and R2? We start by calculating total current. So to find total current, we must find total resistance. This circuit is made up of two resistors connected in parallel. We use product over sum, so our total resistance becomes 6.67 ohms. We divide this into the supply voltage, so our total current is equal to 7.5 amps. So we are done. You get all the marks. We now want to find I2, and we are going to apply current divider rule. We are going to say the opposite resistor R1 multiplied by the total current IT divided by the sum. If we apply this, we are going to get 5 amps. This is our I2, which is this. To find I1, you can simply say our input current is 7.5 minus this, because the current entering a junction is equal to the current leaving a junction. So you must find 2.5, or you can choose to go the longer way, which is the current divider rule, and you say the total current is 7.5 multiplied by the opposite resistor, which is equal to 20 ohms. Then you divide that by the sum of the parallel combination, which in this case is 30. You get the same answer, 2.5 amps. So this is how you proceed, guys. Please take note of this. It can be proved that I1 plus I2, that's 2.5 plus 5 gives you 7.5. And please take note that for three resistors connected in parallel, which is the level you are going to start up to find I1, you simply say total resistance multiplied by the other two combination of resistors, R2 and R3. Take note there is no R1 there. Then you divide by this combination of products. To find I2, take note that there is no R2 there, and you divide by the same sum. To find I3, take note that there is no R3 there, but this sum is the same. This is how you proceed, guys, and I hope you are finding it more and more interesting as we approach. We are now going to look at how to solve series and parallel circuits. As you can see, this is a parallel circuit and R1 is in series with the combination of the two. So how do you go about it? First, you find the equivalent circuit of the two resistors connected parallel, then you add the two. So if you find the total resistance of these two resistors connected in parallel, the equivalent resistance is equal to the product of a sum, which is equal to this. Then to simplify this, you simply add as the two resistors in series, this plus this, and you are done. This scenario is different from the scenario in the previous slide. In this way, we've got two resistors, R2 and R3, that are connected in series. And this series combination is in parallel with this load. Why am I saying it is in parallel? Because the sum of this and this is connected to this junction, which is where R1 is connected, and also they are connected at this junction. So we've got 2 points in common, this point and this point. So we are saying R2 plus R3 is in parallel with R1. Please take note that R2 is not parallel to R1 and R3 is not parallel to R1, but their combination is the one that is in parallel with R1. So to find total resistance, we add the two, then these two are now in parallel. So to find total resistance, now you say R1, R equivalent divided by R1 plus R equivalent. That is product over sum. Interesting. Is our past a worked problem on series parallel circuit. We've got a series parallel circuit. This other one is in series with this parallel combination. So what I'm going to do first, we need to find the total parallel combination. That's product over sum. This is going to give us the total resistance for the parallel circuit. Then the total resistance or other equivalent is in series with 12 ohms. We add, as you can see, the parallel combination is 8 ohms. That's 50. That's 400 divided by 50. Then total resistance is 4 plus 8, which is the other equivalent. Then we find 20 ohm. To find I1 we simply say the supply voltage divided by total resistance, which is cost 100 divided by 20. This gives us 5 amps. So we can now calculate V1 and V2, or even I3. So how do we calculate I2? We say this is I2. We say 40, which is our opposite resistor, multiplied by the input current, which is 5, divided by the sum of the parallel branch, which is 50. Then you get 4 amps. To find I3, you can simply say 5 minus 4. This gives you 1 amp. Or you can go to the current divider rule and you say we are now finding I3. So sorry, this must read I3. This must read I3. I repeat, this must read I3. So we say the opposite resistor 10 times the input current 5 divided by the sum of the parallel combination. You are getting 1 amp. So this is how you proceed, guys.